Okay, hello everyone. Welcome back to another episode of Science and Technology Q&A for kids and others. And I see a few questions that were left over from last time, which I will start off looking at. Let's see, I thought I had answered some of these before. Okay, there's a question here from Alexander about quantum computers and commenting that he's noticed that I've said a number of times that I don't think quantum computers are going to work, but nevertheless, he reads accounts that say a quantum computer with such and such a number of qubits has been created. Okay, let's talk about what quantum computers are, what might work about them, what qubits are, what might not work, and so on. Okay, first of all, how do ordinary computers work? Well, so at some fundamental level, ordinary computers are dealing with binary bits, places where there either is a piece of electric charge or there isn't. And usually all current computers work using semiconductors. And basically what's happening is there on a CPU chip, there might be 1 billion different little tiny transistors. And each transistor has these little places where there's a little tiny amount of charge. It's maybe 100,000 electrons per bit. And if the electrons are there in a particular place, then that means that the computer says that particular bit is a 1. And if they're not there, it means that particular bit is a 0. And then when that turns into what is the data that represents, I don't know, something on my screen, let's say, my screen might have 5 million bytes of information. That's a byte is 8 bits. So that's 40 million bits of information, 40 million places somewhere on my CPU chip where there is some, actually it'd probably be in a coprocessor, but basically in the microprocessor in my computer, there'll be a place where I'm storing the information that there'll be this little clump of 100,000 electrons, maybe a little bit less these days, that represent whether that pixel on my screen is a 1 or a 0. And when the computer is computing things, what's happening is there will be these packets of clumps of electrons are being sort of shoveled through these gates where it'll be like, if there were electrons in this place, but not in this place, then there'll be electrons in this place. And that would be an example of one of the sort of fundamental operations. The most fundamental operation on most computers is the NAND operation that says, if there are not electrons in either of these two places, then make electrons be in this place. And you might think, how can you build up everything a computer does from just that one operation? But that's one of the really neat things that's been figured out through lots of work in logic and mathematical logic and computation, that it's possible to just take that one simple operation, first of all, and go from NAND to all the ands and ors and nots, and then go from the ands and ors and nots to the whole operation of a universal computer. That's all it takes. So that's how an ordinary computer, it's just shoveling around these blocks of electrons and so on, with definite things supposed to be happening. So, you know, the electrons, the lump of electrons, 2 lumps of electrons are there, then there won't be a lump of electrons there at the next moment. And the next moment is usually, most computers have a central clock. Maybe in modern times, it might go at a rate of maybe 2 billion cycles per second, where 2 billion times a second, it says, okay, electrons, go to the next thing you're supposed to do. And that, so every time, at every sort of tick of the clock, you're doing these different operations. But the way an ordinary computer works, it's doing definite operations. It's like there are electrons here and there. Okay, make electrons not be there at the next tick of the clock. Okay, the idea of a quantum computer is to make use of quantum mechanics to say, well, we don't have just one definite thing happening. We have, and this is sort of the big idea of quantum mechanics, which is kind of the mechanics that governs very small things like individual electrons and so on. Instead of having these big lumps of electrons which are going to do definite things, just make it be the case that you're sort of leading the quantum system to do many possible things. And the quantum system can do those things in parallel. And the way quantum mechanics works, it's sort of following all these different possible paths of things that could happen. And only when you've sort of it's finished following all those paths, and we say, well, what actually happened? We make a measurement of what happened. Then somehow it has to kind of decide what really happened and give a definite result. And quantum mechanics, it's sort of a mysterious thing how this all works. It's something we've made a lot of progress recently in figuring out in the sort of this new approach to fundamental theory of physics. A lot of progress in really understanding how quantum mechanics works. Let me give you a sort of an indication of how quantum mechanics works. That's sort of a picture. So imagine the game tic-tac-toe. So you are, playing this game, and you have the X's and the O's, and you start off in some particular way, and there are many different possible games that could be followed. There are many different places the X and the O can be put down, but at the end, either the X wins or the O wins. And this is a little bit of how quantum mechanics works. Actually, the mathematics of how that works seems to be very closely analogous, that in a sense, you're saying we're going to start these things off, and there are many possibilities for what can happen, but in the end, there's a definite result. One thing wins, the other thing wins. The electron is either there or it's not there. But in the middle, you don't really know what happened. And what happens in sort of a quantum version of tic-tac-toe, instead of it being a definite sequence of moves that are taken, in a sense, all possible moves are being taken. And only at the end do you find out whether the X won or the O won. And so that's kind of the idea, is that you follow all these paths in parallel, and somehow the universe is doing that all the time at a small scale, and that's what quantum mechanics really is. Now, the idea of quantum computers is to be able to take advantage of all those parallel things that can go on, to be able to do many different computations in parallel, and only at the end when you're like searching for something, you can say, let's try all these different cases. And if one of them finds what you're looking for, then make that be the result. But you can, instead of trying to do the search by saying, try this, then try this, then try this, then try this, then try this, the idea is do all those searches in parallel. And that's something that the physics of quantum mechanics says you should be able to do. Okay, here's the basic problem from a theoretical point of view, which is, yes, the physics of quantum mechanics says you can do all these things in parallel. They will happen in parallel. But the problem is, when you want to figure out what happened, when you want to do the measurement, there's a whole process that one has to go through in figuring out how to go from the set of parallel things that could have happened to a definite thing that is sort of what actually happened. And that process of measuring things is something that hasn't been well understood. And in fact, in the last 100 years or so, since quantum mechanics was invented, it was invented about 100 years ago now, this process of measurement is always something a bit mysterious. Most calculations that you do about quantum mechanics, about the properties of atoms and things like that, it doesn't really matter how this measurement process works. But when you actually try to build a quantum computer, it really matters that the quantum computer has to do this measurement, has to say, what was that final answer? Everything was computed in parallel, but then what was the actual answer? And what seems to be the case, and what we've discovered, is that process of doing measurement is actually quite difficult. And while the quantum mechanics gives you this opportunity to have all these things be done in parallel, getting from the point where you have all these things that happen in parallel down to, oh, and a definite thing happened, that requires a whole bunch of computation. And it seems like that computation is at least as difficult as what you gain from not having to go through and sequentially do everything and being able to work in parallel. Now, I mentioned how classical computers work, and I talked about these bits and so on, and like a typical computer these days might have, I don't know, let's say, I don't know, 64 gigabytes of memory. That means, can I do the math in my head here? 128, 256, 512. Yes, that means 512 billion bits of memory. Okay, so 512 billion, that's a half a trillion bits. So in quantum mechanics, one's trying to set things up so that one can have information stored at the level of, in these so-called qubits, where a qubit is something that isn't it's always a 1 or it's always a 0. It's something where in that idea of sort of all these parallel possibilities, a qubit can kind of participate in that parallelism. The qubit can be, well, it's a 1 in some situations, but it's a 0 in other situations, all happening in parallel. That's what a qubit is. And people have been trying to build computers with lots of qubits, where in the case of, remember, we have half a trillion bits in your average computer, maybe these days, a classical computer. People are like, we managed to get 10 qubits in our quantum computer. That's the kind of thing one's doing there. Now, those 10 qubits, if they really worked according to plan, they might be quite powerful, because those 10 qubits actually can represent what one's dealing with is not definite ones and zeros, but sort of all possible combinations of ones and zeros. So in 10 qubits, that'd be 1,024, 2 to the 10 possible combinations. So people have different schemes for making qubits. Sometimes they're made out of superconducting, so-called Josephson junctions, which are things that use the quantization of magnetism in superconducting devices. Sometimes they're made of using various kinds of cavities, microwave cavities. Sometimes they're made using features of individual photons of light. There are a variety of different technologies for trying to make these kinds of qubits. And in practice, when people set up these computers, they may be going to lots of trouble to measure the results. They don't really know how much effort it takes to measure the results. What they do know is that after a certain amount of time, there's this phenomenon called decoherence that happens that goes from sort of the quantum effect to, oh, it isn't really operating in a quantum way anymore. And that happens fairly quickly in many of these computers. And that's sort of a trade-off between doing that and measurement and so on. And it's a bit unclear sort of what the resource use really is in these computers. And that's the big issue, is from at least a theoretical point of view, is it the case that you can sort of get advantage from having the physics of quantum mechanics operate, and that you don't lose that advantage through all of this stuff about how you measure the results and the decoherence and all this kind of thing? One doesn't know that yet. And one certainly doesn't know that for sort of the case of most interest, which is lots of qubits, really difficult computations. My guess is it's not going to work out from a theoretical point of view, although in practice, representing bits of information using, for example, sort of single electrons or single amounts of quantized magnetic flux, these kinds of things, that may be super efficient relative to our current scheme of use 100,000 electrons per bit. And so the physics of what's going on may be highly interesting, even though the kind of theoretical advantage of, oh, quantum mechanics makes everything work in parallel may not pan out. So that's kind of the story, I think, of kind of the what these qubits are, and kind of the picture of how quantum computers might work. And there are only very specific kinds of computations that people imagine might be able to be done sort of more efficiently in a quantum computer than an ordinary computer. It's been a surprisingly small set of computations, basically 3. Factoring integers, doing certain kinds of searches, and simulating actual systems that operate according to quantum mechanics. There's only 3, I think, which have been seriously considered there. And it's surprising that in the course of many years, there haven't been other kinds of computations that one can sort of even theoretically say could be much more efficiently done on a quantum computer. I should say a sort of footnote to this. There are some different kinds of things that get the brand of quantum computer. The thing I've been talking about are so-called quantum circuits. There's a different approach, which is more like a quantum spin glass, and maybe I can talk about that another time if people are interested. That's kind of not the quite mainstream way of doing quantum computing. All right. Let's see. There's a question from Martian Lemon. How do we know there are more than 3 dimensions? So in our physical universe, so far as we can tell, it's pretty close to there just being 3 dimensions. Just move around in, left, right, front, back, up, down. The question of whether, as a theoretical matter, doing mathematics, you can imagine different numbers of dimensions, 5 dimensions, 15 dimensions, even 3.5 dimensions. That's a different question. It's not too hard to understand that. Let me give you an example. I'm going to say it in words. It'd be easier if I used a computer, but I think I can say it in words. Let's say you draw a picture of a square. You got 4 points, you join them up. Okay. Let's say you draw an outline of a cube. You've got 8 points, you join it up in a cube. Let's say you've just got 2 points. You can join them up in a kind of one-dimensional thing, just a line goes from one point to the other. So you've got the one-dimensional thing, 2 points, the two-dimensional thing, 4 points joined in a square, the three-dimensional thing, the 8 points joined in a cube. What happens if you have 16 points? Well, there's a way of joining them so that every point is joined in that case to 4 neighbors. In the case of the cube, it's joined to 3 neighbors. In the case of the square, it's joined to 2 neighbors. If you go to 16 points, you can join every point to 4 neighbors. And so then what you'll get is this kind of network that you can think of as representing a 4-dimensional cube. Now, if we make a picture of it, we're just making a picture where we have projected the 4-dimensional cube and we're just seeing it in 2 dimensions. Just like if we draw a cube on a piece of paper, we're taking a 3-dimensional object and showing it in 2 dimensions. But you can do that perfectly well for a 4-dimensional object or a 5-dimensional object or a 10-dimensional object and so on. And that's the sense in which one can imagine other numbers of dimensions. Now, there's a question in physics of whether maybe the physical universe doesn't have exactly 3 dimensions, but maybe more. There's something that came out of the thing called string theory, which is kind of a long-running theory that's had a couple of different sort of runs and over the course of the last 60 years or so. And one of them, it was kind of an idea for how gravity and quantum mechanics and things should all fit together. And it had the problem that when you worked out the math, the thing was it just didn't make sense unless the number of dimensions of space was either 26 or 10. And so that's like, there's something wrong with that because our actual space plus time is like 3 + 1 dimensions. That's not 10 or 26. How do we understand this? That was something where mathematically the theory said, it should be in 10 dimensions. Then there was sort of a question of, well, could that actually be right? Could it be that there are sort of, let's say, 6 other dimensions that are all rolled up in little balls and we aren't sensitive to them? To me, that's probably a sign that the theory wasn't really on the right track. It's usually a bad sign when one's theory sort of says, and there's something should be true about the world, and you can plainly see it's not. But the mathematics of string theory is very elegant and actually even relevant to the theory that we're making. And so people sort of pressed forward even despite that problem and found all sorts of interesting mathematical physics results. Let's see, a question here from Ettore. What is quantum tunneling? Okay, let's say you are trying to roll a ball over a hill. You make the ball roll, if it has, and then you have this hill. And the question is, if the ball has enough momentum and enough kinetic energy, the ball will kind of, you can get it to kind of, or let's say you're doing, I don't know, let's try and be mod and say you're doing skateboarding or something, and you're going at a certain speed. And the question is, can you get over that hill based on the speed you're going at? If you're going fast enough, you'll just be able to, you'll have enough energy, you can get to the top of the hill, it's all good, and you go down the other side. Okay, so that's kind of the view. If you have enough energy, you can get through this kind of you can get over the hill. Okay, well, there's this funny phenomenon that happens in quantum mechanics, that even when you don't have enough energy to get over the hill, there is a slight chance that you might get over the hill anyway. And this is something that doesn't happen for, big people like skateboarders, so to speak, but it does happen for individual particles, like the kinds of particles that exist, like protons and neutrons, and particularly clumps of protons and neutrons called alpha particles that are actually helium nuclei, 2 protons, 2 neutrons. The question is, even when there's this kind of barrier to an alpha particle getting from one place to another, can it do it? And the phenomenon of quantum tunneling is, well, actually, it depends on the amount of energy you need to get over the barrier. But if you are below the barrier, even if you're below the barrier, there's still a slight probability that you can get over that energy barrier. The probability decreases exponentially with the size of the barrier. That means if you multiply, let's say as you increase the amount of energy, just you go 1 to 2 to 3 to 4 to 5, you're going down by factors of some constant. So it might be 10 times less likely. If the barrier is twice as high, it might be 10 times less likely. If it's 3 times as high, it might be 100 times less likely, and so on, to get over the barrier. What actually happens in quantum tunneling? We actually have an understanding of that in our new theory of physics. It would take me a little bit to explain how that works. Essentially, what happens is that instead of sort of going through the physical space that goes from one side of this barrier to the other, you're going through this thing we call branchial space, which is the space of quantum states, and it's kind of an abstract space. And that's kind of what's happening in quantum tunneling, is that you're kind of getting from here to there, not by going through physical space, but by going through this branchial space. But it would take a bit more explanation to say how that works. Now, what's the significance of quantum tunneling? One of the pieces of significance is, because of this exponential effect, a small change in the potential barrier can make a huge change in the chance that quantum tunneling happens. That has a big effect on radioactivity. So radioactivity is the phenomenon where an atomic nucleus becomes unstable. So for example, a very famous one is uranium-235. It's uranium with 235 protons per its neutrons in its nucleus. Uranium-235 kind of just spontaneously falls apart. The nucleus is not, those protons and neutrons are not bound together strongly enough, and after a certain amount of time, uranium nucleus just self-destructs. Well, there are other nuclei that fall apart by emitting an alpha particle. It means that 2 protons, 2 neutrons just sort of get thrown off from the nucleus. And that's the mechanism for radioactivity. One of the very surprising things is that there are radioactive elements that are alpha emitters that have lifetimes as short as a trillionth of a second and as long as 1 billion years. Huge range of different kinds of lifetimes. So the lifetime is determined by what's the chance, what's the rate at which these alpha particles get emitted from the nucleus. Well, turns out that the basic phenomenon of alpha decay, alpha radioactivity, is related to quantum tunneling, and that huge range of different lifetimes is a reflection of this exponential phenomenon that I was telling you about before, that even though these different elements just have a little bit different energy barriers, that because quantum tunneling is an effect that depends exponentially on the energy barrier, the effect on the lifetime is immense. And so it can range from 1 billion years down to a trillionth of a second. That's kind of a little bit on quantum tunneling. Let's see. Okay, there's a question here. There's a question here from Brian. Why is the 3-body problem so hard to solve? Okay, so first, what is the 3-body problem? So imagine the sun and the earth. Force of gravity holds the earth in its orbit. The earth goes around in a nice orbit around the sun. And what was figured out back in the time of Kepler and Newton, back in the 1600s, is that the earth follows an ellipse around the sun. Not quite a circle, it's very close to a circle, but it's not exactly a circle. It's an ellipse, which is like a circle with two different radii in the two different directions. And it follows an ellipse with the sun at sort of the one focus of the ellipse. And there's a nice set of mathematical formulas that describe that ellipse, and that's the two-body problem, the sun, the earth, two bodies. Now, the real situation is a bit more complicated, but there's a good idealization of that, which is just this two-body problem. Okay, what happens if we think about the moon as well? That's a three-body problem, because there's the gravity of the sun acting on the earth, there's the gravity of the earth acting on the moon, but there's also the gravity of the sun acting on the moon, and the gravity of the moon acting on the earth, and all these systems are all interacting with each other. Well, it just turns out that the mathematics of the three-body problem is just a lot more complicated than the mathematics of the two-body problem. How can we see that? Well, let's see. There are probably a few facts to say. So in the two-body problem, first of all, the path that's followed is always an ellipse. Whatever happens, it's always an ellipse. Actually, if the body escapes its orbit, it can be a parabola or a hyperbola instead. But if it's in orbit, it's an ellipse, and that's it. In the case of the three-body problem, there can be just all kinds of different things that happen. You see these pictures of the three-body problem. I've made plenty myself, where one body comes in, that there are two other ones that are orbiting, and this third body just comes around, and it looks like a big scribble. And it takes a really long time even for it to have a final outcome. So the final outcome might be, let's say you've got a binary star system, which is two stars orbiting each other, and another star comes in, and it comes near that binary star system. What's going to happen? Well, one thing could happen is it could capture it. It could end up in a ternary star system. Another thing could happen is it could break that star system apart, and all three stars could go off to different places. Lots of different things could happen. One of the things you see when you do simulations of this is that sometimes these stars go around in this really complicated dance for a really long time, and you can't figure out what's going to happen. So one of the things that you can see is that the amount of time, if you say, I'm going to do my simulation, and my simulation is going to last for the equivalent of 1,000 years in the real life of the stars, so to speak, it may not be clear what's going to happen after 1,000 years. And you say, well, okay, I'll wait 1,000,000 years. Still, they're dancing around doing complicated things, not clear what's going to happen. So that's one of the problems. And that's kind of one of the reasons so that leads to the possibility. It's like if you're running a computer program and somebody says to you, what's this program going to do? You say, well, I think it's supposed to do this. Maybe it'll have a bug, maybe it won't do that. It's very easy to get a program where it's very hard to foresee what the program is going to do, and where really the only way you can work out what the program is going to do is by just running it and seeing what happens. The three-body problem is probably an example of something which works that way, which has a phenomenon I call computational irreducibility, which causes that effect to occur. Now, I should say that one of the things that happened in in the 1800s, the solution of the three-body problem was like a top problem of mathematics and physics. It was like, that was the big prize. Can you solve the three-body problem? And so people tried very hard to do that. And one of the things that they tried to figure out is, when you solve the two-body problem, the answer comes out in terms of mathematical functions like sines and cosines, and also actually so-called elliptic integrals. But it's basically pretty civilized things, like at least the sines and cosines are things you'd learn about in a trigonometry class or something like this, and civilized kinds of things. Sometimes equations, you can write down equations, and it can be really hard to solve those equations, and it may be the case that you can't solve those equations using anything that you already knew about. So for example, quadratic equations, x squared minus 3x plus 2 equals 0 or something. Equations like that, there's a formula that says, x equals, let's see if I remember the quadratic formula, minus b over 2a plus square root of b squared minus 4ac over 2. over 2a, yes. Sorry, I had to actually work that out. In any case, that's just a formula for the solution of any equation that involves x squared and x, something involving x, and a constant. It's a formula in terms of square roots that lets you solve it. If you go up to the equation x cubed, x times x times x, etc., what value of x solves that? There's also a formula for that. It's a big, long, complicated formula. It involves cube roots. Same thing for x to the fourth. You can write down big, long formula that involves fourth roots. Okay, what about when it's an x to the 5 in there? People thought about that for a long, long time. The case of the cubic and the quartic, they were solved in the 1500s, and people up until the 1800s were thinking, can we solve the quintic, the equation of with x to the 5? And nobody figured out how to do it. And eventually, a young fellow named Évariste Galois came along and basically proved, sorry, you just can't do it. There isn't a formula for the solution to a quintic involving, let's say, fifth roots of things and so on. There's no algebraic formula for the general solution to quintics. That was proved in the 1830s. Then by the 1880s, 1890s, a similar result was proved for the three-body problem, that it's not possible to have, the official term is algebraic integrals of the motion, that it isn't possible to basically write down a solution for the three-body problem in terms of algebra type functions. If you want to write down the solution to the three-body problem, you have to invent some new exotic kind of mathematical function to describe that solution. And there's not a guarantee that you can compute what the values of those solutions are much more efficiently than by just running the three-body problem. So that was the main result, is that you can't solve it as an algebraic thing, and it can take sort of as long to work out what happens as it would to just run every sort of step in the evolution. And that's, I could probably, let's see if I could, gosh, do I have any chance to be able to sort of derive for you in real time the fact that there are no algebraic integrals of the motion for the three-body problem? I think not. I think it's a bit too mathematically complicated. But so that's a response to that. Okay, here's a question, different kind of question. Oh boy, we're getting so many of these. You guys ask such interesting questions. All right, this is a bit more of a history question from Parmenides. Who is your favorite Manhattan Project scientist? Says, I was reading about Stanislaw Ulam. Did I ever meet him? Yes, I did know Stan Ulam. Okay, first bit of background history. So for people who don't know it, the Manhattan Project was a big project done in World War II in the US. The goal was to make an atomic bomb, which was successfully done in 1945, and was kind of a great sort of success of science to be able to do that. It went from the discovery of radioactivity in the 1910s, I guess, to the realization that it was possible to make energy from nuclear processes. That sort of was realized in the 1930s, 1940s, to then the idea you can make an atomic bomb and then to actually build one. And it was built in a rather small amount of time, maybe 3-4 years, by this it was sort of a large collection of physicists who were involved in doing this. It was a project led by a person called Robert Oppenheimer, who was in fact also the person who figured out a lot of stuff about black holes and the collapse of stars and so on. But his probably most famous thing was that he was the scientific leader of the Manhattan Project. So a lot of physicists who I have known worked on the Manhattan Project, and it was a strange thing to have created nuclear weapons, and I think many of them had. It wasn't at all clear what was going to happen, given that, one had invented this technique for basically, generating extremely powerful weapons. What was going to happen? Fortunately, since 1945, these weapons haven't been used again, and there's been surprisingly limited there's a limited number of countries that have the technology, and it's a complicated stack of technology that has to be built to make a nuclear weapon. It's a complicated supply chain of the kinds of materials you need to do it and so on. It's been kept rather limited for a surprisingly long time. So in terms of the physicists who worked on the project, well, there were many. And I knew many of them. Few of them are alive anymore. The focus of work in the US on the actual atomic bomb was done at Los Alamos National Lab in Los Alamos, New Mexico. Strangely, even when I was first in the US, I think Los Alamos was a not marked on maps town. So it was like, for all practical outside purposes, it did not exist. I was for a while a consultant at Los Alamos National Lab in the early 1980s. So that's part of how I got to know a bunch of these guys who were still at Los Alamos. Many people had left Los Alamos. I would say, oh gosh, I'm going to forget lots of people, but a couple of notable folks from there. One was Richard Feynman, who I knew quite well, who was a physicist who was particularly notable for having understood a lot about quantum electrodynamics, the interactions of electrons with photons and so on. His job in the Manhattan Project, he was a young guy, let's see, he was just in graduate school when the Manhattan Project happened. And his job was to run the pool of human calculators. Back in the days of the Manhattan Project, they didn't have electronic computers, they had only primitive sort of desk calculators and things. And Dick Feynman's job was, when you want to compute you want to compute characteristics of what was going to happen in a nuclear explosion, for example. Well, how did you do it? Well, you had to actually do computations, and that was done by a pool of people who had these calculators and would do it, and there would be these different methods for calculating different things. And Dick Feynman told me, one of the terrible things was the first test of an atomic bomb was done in the desert in New Mexico in, I think, 1945, maybe 1944, but I think 1945. They had calculated one of the potential risks was, because nobody had ever detonated a nuclear explosion in the Earth's atmosphere. And one of the things that was a sort of really bad case scenario is maybe detonating a nuclear weapon in the Earth's atmosphere would ignite the atmosphere. That is, it would just start a reaction where the whole atmosphere would burn. And that would be sort of super bad news, end of life on Earth, game over, really bad. And so that was one of these cases where you really had to get the calculation right. And Dick Feynman his group had been one that was sort of part of that process of doing that calculation. And he was like, he was very, they were like, well, we think it's going to come out that it's not going to ignite this atmosphere, but we're going to test this thing anyway. And fortunately, as we know, it didn't ignite the Earth's atmosphere and all was well. But that was a case where a very high stakes calculation that had to be made. Other people who worked on, a lot of people. Dick Feynman's thesis advisor, John Wheeler, was another person who worked on two people to mention, Edward Teller and Stan Ulam. I didn't know Edward Teller particularly, although I did meet him, and I know lots of people who knew him. He became a major figure in kind of defense technology in the U.S. One of the things that are very important actually in the hydrogen bomb. The first atomic bomb used in World War II was a fission bomb based on breaking apart nuclei of uranium and plutonium. The more powerful bomb that was invented a few years later was the hydrogen bomb. And no, actually, I'm telling you the wrong history here. It's correct about the hydrogen bomb, but actually, the thing I'm going to tell you is actually about the original atomic bomb at Los Alamos. So one of the key things that you need to do in making an atomic bomb is you've got to get a large amount of uranium into a small volume very quickly. And the way you do that is you detonate an ordinary explosion with ordinary high explosives in a kind of a shell around the uranium, and that pushes the uranium together and makes the thing get to be dense enough that it can have a nuclear reaction and nuclear explosion. And so one of the problems is, how do you get all these pieces of uranium pushed together sort of quickly enough? And you don't want it so that the thing can kind of, you push it together one way, but it squirts out another way. And so the thing that had to be invented for that was a thing called the implosion lens, which is kind of a way of placing explosives in a pattern and with material so that things will be just pushed together. They will just squash down to be so that you get this sort of spherically symmetric implosion rather than something that squirts out in one direction or another. And so that was sometime it was, I guess, the Ettore Ulam device was the thing that was sort of the invention that was this implosion lens. And of course, I heard many people say, oh, really, it was all Teller's work. Oh, really, it was all Ulam's work, et cetera, as unfortunately tends to happen in the science world. But that was sort of an important invention. Stan Ulam was one of the people involved in that. As I say, I did know him in the last few years of his life. He died in 1984, I think. Well, you know, it's always so hard when one knows people. Yeah, he was a what can I say? Well, one of the things he did, he was a kind of really particularly a mathematician. And, you know, for him, it was like, can you take a problem and turn it into an elegant piece of mathematics, particularly a piece of kind of discrete mathematics that just involves integers and so on. He did that a bunch of times. And one place he did that was something that sort of intersected with my own interests, is in these things called cellular automata, which are these sort of simple programs that are based on just things with black and white squares and so on. And Stan Ulam worked on those things, and I interacted with him a bit about those things late in his life. It was right around the time I was working on them. In fact, I once organized a conference at Los Alamos in, I think, 1983, and Stan gave the after dinner speech at that conference. I have to say, I have to tell you one of these scurrilous stories, you know, which is kind of a funny thing. But right around that time, it was some article that I wrote for the Los Alamos Science magazine, and there was a sort of additional add-on, which was about the history of cellular automata at Los Alamos, which is quite interesting. And I was like, I was always impressed because the editor of this magazine, you know, had, you know, that article appeared under her sort of byline, and I was always rather impressed that it seemed like a very nice piece of scientific history. Okay, so now that was 1983 or something. So now many, many, many years later, I'm doing history research for a big book I was writing, and we are interested in getting some material from the Stan Ulam archive, which is, I think, in Philadelphia, the archive of all his papers. And the person who was working with me sent a message to the archivist there saying, you know, can we get this information about this particular thing? And the archivist says, oh, well, actually, there are some letters in the archive about your boss. So, of course, the person who was working on this for me was like, well, sure, send those to us too. And what became clear from those letters is that Stan had been kind of like well, you know, there's all this interesting history, and you know, these young people don't know about any of this history. Let's put this history out in this magazine, but he didn't want to, even though he wrote it, he didn't want to sign it himself. It was like, let's get the editor of the magazine to sign it instead. So that was kind of a little bit of a disappointment to me in terms of the origin of that, because it actually would have been interesting to know that was sort of Stan Ulam's view of the history back at that time. Anyway, I could tell you lots more about these people, lots more. Let's see. Oh gosh, so many questions here. Oh, there's one here that I will. You know, these questions about history, I'm really happy to talk about these. I love talking about history. I have noticed that the old are typically more interested than the young in talking about history. And maybe I will do a quite separate session like this about history. And we'd be interested in some feedback about whether that would be interesting. Let's see. There's a question from Udesio. Have you ever considered teaching other subjects besides math? What subjects? You know, I have never really taught anything. I was briefly a professor 30-something years ago, and I think I was not a, I don't know whether I was a very good professor. I think one of the problems was because I had gone through school without really, I didn't really go to very many classes from, you know, I kind of left high school when I was 16. I kind of went to college, but I didn't have to go to any classes and didn't. And I really didn't go to any classes ever. And so then, you know, a few years later, there I was as a professor, and it's like, okay, go teach these classes. But it's like, I didn't really know what to do. And I think my kind of high point or low point was I ended up, back in 1986 or so, ended up saying, I'll teach a class about physics for non-scientists. And I just had a very strange view, I suppose, of what I should talk about there. Well, I think people seem to enjoy the lectures, although people started coming who weren't part of the class, which is always that's a good sign. The bad sign was that people were like, you know, you didn't explain how to do the homework. And I remember the very last, this was at University of Illinois, and the very first question on my first sort of homework was estimate the number of ears of corn in a typical cornfield, which I thought was thematically relevant. And this was not appreciated because it was like, but there's no specific procedure for doing that. And it's like, well, you have to kind of think about it. And you know, it seems like it's fun to try and learn how to think about stuff. But anyway, my days as a genuine professor were truncated by the fact that I decided that it was better to spend my time running companies and things. So I haven't really had much opportunity to teach anything. In recent years, I've become much more interested in these kinds of things. I started a few years ago, particularly where I live in Massachusetts, teaching some middle school kids and so on about computation. I found that pretty interesting. You know, it was actually a great way, has been a great way for me to learn more about how to make our Wolfram language and so on easier to use, because it's a case where I actually can see people, you know, using our products, that's fun. And I guess that I've found, you know, I just started with this pandemic, kind of doing these live streams, trying to explain stuff, and I hope you guys get something out of it. I know I get something out of it because I think I've gotten measurably better. You can judge for yourselves at explaining things as a result of doing these live streams. Because usually in most of the things that I do, it's like people ask me some question about you know, the future of fusion energy. I see one here which I'd love to answer, but I'm not going to have a chance today. And it's like I have to try and think through, you know, how do I take the things I know and break them down to the point where I can actually explain them. And it's been really interesting to sort of learn how to do that better. I see some questions a little bit about history here. Someone's commenting on Glenn Seaborg. I did not know Glenn Seaborg. It's the only person who has ever had an element named after him while he was still alive, which is in recognition of the fact that he was so involved in generating new chemical elements by nuclear processes and so on. It's a question about from Luis about what do I know about Ettore Majorana. I don't know that much about Ettore Majorana, an Italian physicist from the 1930s who was a sort of very promising young physicist who disappeared. He got on a boat going to Sicily and he never got off at the other end, and nobody knows what happened to him, which is sort of a sad story. But the work that he did has actually become very popular in recent years. He was interested in well, kind of things a bit like electrons, but that would have a different way of being, of operating with respect to, particularly with respect to spin. And it's become very popular in recent years. So his name is sort of these Majorana fermions are things that get heard about quite a lot these days. Oh my gosh, there's questions, so many interesting questions here. All right, I've got to do allocate more time to this. Unfortunately, I'm supposed to go to something else in a minute, which is actually also a live stream about more what I actually do for a living, designing functionality for orphan language. But there's a question here about music theory and composition. Do I know about Dmitri Tymoczko? Is that, no, I'm not, that's not, I'm not saying the name right, but professor at Princeton, who I have certainly met, and his work on sort of understanding musical structures and mapping them into mathematics. Great topic. Let's talk about it another time. And at least I see one question here where I definitively don't know the answer. It's asking about Hurwitz's automorphism theorem, and I don't know what that is. So that's so I'm sorry about that. All right, I think a lot of really interesting questions here, which I'm going to have to take up another time. I'm just, there's one here from Lauliet about neurons, nerve cells in our brains. Do they operate quantum mechanically? Do they operate in other ways? I will say that my strong suspicion is that quantum mechanics is not important in the things that actually affect the way that we think about stuff. It's probably important in the details of how neurons work, but almost certainly the actual electrical processes that communicate information between neurons don't depend in detail on quantum mechanics, and they can be represented without that. But I'd be happy to talk about that another time. Well, I should wrap up here. For those who might be interested, I am doing another live stream about, I think I'm talking about working with our team on design for algebra and calculus functionality in Wolfram language for our upcoming version. But otherwise, I have to sign off here. And nice to chat with you guys, and I look forward to doing it again next week. All right, so bye from